nuclear properties. And today we carry on with nuclear properties, and we introduce the nuclear force. So as I say, every chapter has a particular plot here that I'm interested for you to remember. In this case, this is the nuclear force potential, the nuclear potential, the nucleon-nucleon potential interaction. And as I mentioned during one of the colloquiums that I gave recently, and hopefully some of you watch it, the nucleon-nucleon potential, the nucleon-nucleon interaction, or the nuclear force is very difficult to pin down to a definite form because it's very complicated, and there are many different potentials with many parameters which do the job. They are called realistic potentials, but there are many of them. It's not like we have a single Coulomb force or gravitational force. We have many ways of extracting what people believe is the nucleon-nucleon potential, and this comes from elastic collisions. So this comes from data, extracted from data, and we fit what we call the phase shift to the available cross sections. I mean, this is more advanced subject, but I want to let you know that I posted also on chapter 2. Right here, I posted the lecture notes that we're going to follow, and I want you to here at the beginning we introduce a little bit of the issue with the nuclear force. As I mentioned in one of the colloquiums, more man-hours have been given to the problem of the nuclear force than to any other scientific question in the history of mankind. This was said by Hans Bethe in Scientific American. Hans Bethe is a Nobel laureate, and we know what is the situation is very complicated. Not even the experts know the nuclear physics, so it's hard for you guys to understand what we have learned so far. In this chapter, we summarize also a little bit of what we learned before. Again, it's important that we go through Crane first chapter, and we read that in detail. And then here we have about the Rutherford experiment, some elastic collisions, that some nomenclature, basically this formula that you use for determining the nuclear radius, the range of the nuclear force. Actually, so the nuclear radius, the size of the nucleus, from this plot that we saw the other day. There we go, for silver and tantalum. And this is what we introduced last week, and everything is specified here. But today, we are going to check the range of the force. What is how like the sun attracts the Earth very far away, or attracts comets which are even farther away. That we say is a long range. The gravitational force is a long range force, right? The same thing for the Coulomb force. They all have a 1 over r squared, the force distribution. And here in nuclear physics, what do we know about that range is our next question. So I want to go back actually to this plot that we have right here. This plot is the one I want you to understand. And this is what is called actually the long range of the nuclear force. This is the nucleon-nucleon potential as a function of distance. As you can see, here you have a positive potential, which results in a repulsive core. So if you put proton and neutrons very close to each other, they repel each other. But above about 0.5 Fermi, this is a negative, which is attractive. Like in any subject that you have gone through in classical mechanics, a negative potential involves attractive potential, and a positive one involves a repulsive potential. So this is the complication. Here we have, in the simplest case scenario, we have the 1 pion exchange. discovered by Yukawa, Hideki Yukawa, the first Japanese Nobel Prize winner. And then the situation becomes more complicated, and we have two pion exchanges, many meson exchanges. And this is actually what I explained in one of the colloquiums. This is our current understanding of the nuclear force, is that you have a proton, a neutron, right? And they are going to interact, going to get close to each other, and they're going to interact. In that interaction, there's an emission of a particle, which is a pion. So pi is the pion. I have a mass of about 140 MeV C squared, right? This is the particle, they scatter with each other, and this is the way they go. But in the process, there's an exchange particle. That exchange particle is what has been observed, and the same thing happens when you have a proton or electron and electron. There will be an exchange particle, which is the photon, right? The photon will be the exchange particle, or the electrons with electrons, or protons with protons. So this is the understanding of nuclear forces. There's always an exchange particles once these protons, electrons, or in this case, nuclear force is a pion. Once they interact, there's always an exchange particle. And remember, in the colloquium, we mentioned this like this was the case of two people on a boat, right? And this guy has a ball, and he's sending it to this fellow, and this fellow catch it. So there's a recoil of this fellow, there's also a recoil of this guy. So there's an exchange of a ball, but these two guys change because they were interacting through this particular ball, right, in the water. So basically, this is the idea of an exchange particle, and this idea leads to, as I say, the nucleon potential, which we are calling here PR, and this is R. There will be more complicated exchange particles. Many particles will be exchanged, but as we are interested here, this is the Yukawa potential, and here this is proportional to E minus mass of the pion R divided by R. So actually, I was, and this is, as I say, is the long range interaction of the nuclear force, and this is called the Yukawa potential. Okay. So now, a little bit of history. This doesn't do us bad. So Hideki Yukawa, as I mentioned before, was the first Japanese theoretical physicist who was awarded a Nobel laureate, and he obviously has a very strong influence in Japanese science, physics in particular, because that was for Japan to break history in science, to have always a Nobel laureate give you, this was 1949, give you belief, and this is what eventually we need to achieve here in South Africa, many countries, to speed up the process of believing and transformation. How do we believe? By someone showing us the way and someone setting up very high standards. Actually, I went to the Yukawa Institute. I was just checking this morning for theoretical physics. It's in Kyoto. It's a beautiful place, the old capital of Japan, with lots of temples. And this is actually where I went there in 2001. I just realized here that these were the supplements and the proceedings of this conference that was hosted at the Yukawa Institute, and there was my first publication. Here we go. Was published in 2002. Over here, you can check that. Just out of curiosity, I forgot about this, and this morning by looking through the March 1st of March of 2002. So this is my first, also one of my first talks in an international conference. So now the main question that we are aiming at is understanding what is this range of the nuclear force. What is the range or delta X, between protons and neutrons, protons and protons. So how close do they have to be, or how far away they have to be? So first thing is, as we go increase R here, right? This potential will go slowly to zero. So let's see now, and let's use the uncertainty principle. Let's use Heisenberg's uncertainty principle to deduce what is the range of the nuclear force. So as I say, we have the interaction of these protons, neutrons, right? These particles get close to each other, they scatter. Here is before, and this time goes this way. So here is the neutron scatters, and then here's the proton before and after, right? This is called a Feynman diagram. And there's an exchange particle, which is a pion. And we say that the mass of the pion is about 140 MeV per c squared, right? So then we apply the uncertainty principle. The uncertainty principle tells us that delta T is, let's say it's about h4. Okay, so now what we need to know is actually from here, we're going to deduce what is delta X, which is this range that we want to investigate, right? Delta X, so that's our question. Our question is to deduce the range of the nuclear force. It is clear. You can always send me some messages, so I understand that you are following me. Everything is okay so far, right? Correct? Okay. So if there's no more questions, I'll keep going. And we're going to use the equation for the relativistic energy, which is P squared C squared plus M of the pion in this case, C squared, actually M squared C to the 4. And this is the relativistic energy. So in this relativistic energy, we are going to assume that PC is much smaller than MC squared, which is the rest mass. So curiosity out of this equation here is that E will be equal plus minus, there will be a square root of P squared, C squared. So there will be a plus minus solution to this energy, which Dirac investigated, and this is how Dirac concluded that there was the possibility of antimatter. So because there was a positive and negative energy, And this is a footnote I want to make here for you to understand that the relevance of this equation. So now, if we assume that the rest mass is the dominant part of in the kinetic energy, this energy reduces to the well-known Einstein's formula, right? So, assuming Einstein's formula, we deduce that delta T is about h bar times mc squared. So, open a new one. So basically, we have the delta T is about h bar times mc squared. So in this process, in the exchange of the pion, this process cannot go faster than the speed of light. So from here, we're going to assume that, and we're going to say that delta x will be about h bar mc squared, which is the time, times the velocity of light. So delta x will be approximately h bar over mc, right? So we assume that this will give us the maximum range of the nuclear force because, as I say, nothing can go faster than the speed of light, right? So during this exchange of this interaction between the proton and the neutron, or the proton and the proton, or the neutron and the neutron, right? It's not always proton-neutron. So we have that delta x is finally given by h bar mc. So now we know that the mass of the pion is equal to 140 MeV per c squared. And here we're going to introduce a very important constant, which is h bar c equal to 197.3 MeV Fermi, right? And we are going to just substitute here, and the range of the nuclear force will be equal about h bar c over m c squared, because we are multiplying up and down, by c, and this will be equal to 197.3 divided by about 140 MeV. So the MeV and the MeV will cancel. This c squared with the other c squared here will also cancel. So this will give us the range of the nuclear force in Fermi, which is about 197.3 divided by 140 is about 1.4. So this is the range of the nuclear force, the maximum range of the nuclear force, and this is the range somewhere here in this plot that we showed before. This is the long range of the nuclear force is somewhere in this slope coming towards zero, right? So basically, this is the range according to Heisenberg's uncertainty principle. The maximum range of the nuclear force is probably a little bit bigger than that, but around 2 Fermi, and then after that, the nuclear force basically vanishes, right? So in our way to understand concepts, and now you can see why when we deduce the radius of tantalum or the radius of silver, we came with delta x about 1.5, and we assume that, but now you know why we are assuming that the range of the nuclear force is very, very, very short range. However, I don't want to go into more depth at this stage. Basically, this is what you want to take out of this about that we have a repulsive core and we have a short range. Here we have around 1.5 Fermi. Here around 0.5 or 0.3 Fermi actually. This is a negative, is attractive, positive is repulsive. And here we use the Yukawa potential, which is n pi r over, right? This is the range of the nuclear force is very short, and we have reduced it by applying Heisenberg's uncertainty principle. So that's the end of this point. And now I wanted to share with you something else. I want to ask questions. I want you to think about questions. And I want to tell you about the difficulty of, here there's a similar problem where you have someone came across the similar problem of using the uncertainty principle to deduce the strength, in this case, of the nuclear force. So please, can anyone help out? They have come across a solution which I think is not correct as far as the calculations are involved. This is the danger of looking for things in Google and coming to understand. So two things I want you to get out of this picture. The first one is that there's a big danger to go through Google and find solutions to problems. This is a similar case where you can deduce the range of the nuclear force. And here a little bit below, this guy answered the questions, but he came to the point that this is not the right solution. And thirdly, I want you to remember these units that we have been using so far, which are always in Fermi, as you can see, an MeV, right? They're in Fermi because generally the radius of the nucleus, of any nucleus with a mass A, mass number A, is equal, as you know, to 1.2 A to the 1/3 Fermi. And because the excitation of the nucleus is generally in MeV. Also, we have in KV, QKV for X-rays, but generally, or for some gamma rays, we have lots of gamma rays within the KV range. And but basically, this is why we have these questions, H bar C, about 197.3 MeV Fermi. We also mentioned the other day E square equal 1.44 MeV Fermi. I generally don't memorize these things, so you need to check, although at least once I use them quite often. Or for instance, the 931, as we also mentioned, 931.494 MeV per C square, which has an atomic mass unit, or U, as they call it in the books. So you get atomic mass units from the mass of tables, and from the tables you deduce what is your mass in this. These are the units that we always want, right? So we always want C square, F Fermi, H bar, but in these units that we have here, not on these ones. As you can see, there's 10 to the minus 20, 10 to the minus 14, the joule, what mass of the neutron is such and such. You see, this is the mass of the neutron, 10 to the minus 27 kilograms, or it's about 1 GeV, right? Which is 1000 MeV, right? So it's always easier to remember 1 GeV than 1.67, 10 to the minus 27. I will never remember this number. So this is what, and then also I found here, I posted this on a Canva. Here we go, this link, which I also found very interesting, where you can deduce the range of the nuclear force, as we just discussed. There's a little calculation on top of that, which is given here. And here you can have the mass in MeV per C square, let's say 40. So the range is considering actually h bar over 2. You see, it's considering the minimum possibility for the uncertainty principle. So obviously you get a range which is half 10 to the minus 15 meters, which is a Fermi, 10 to the minus 15. So it's basically 0.7, half the range that we have deduced here. But in our case, we use this uncertainty principle, this equation, rather than h over 2. Again, this is an approximation and just roughly tells us about the range of the nuclear force, which cannot be determined precisely, as we know, because of the same uncertainty principle that prevents us from calculate the range of the nuclear force precisely. So now I'm going to stop sharing here, and I see questions. Do we always assume that PC is less than mc squared? Yeah, in this case we can assume that, but it depends. It depends really on the velocity of the particle and the linear momentum of the particle. Say, for instance, for the photon, all the energy will be p squared c squared, right? Because the photon has no mass. So for a photon, a massless photon, everything will be the energy, the kinetic energy, or the energy, the momentum energy of the photon. So for the photon in particular, it will be only E squared equal to p squared c squared. So it depends on the particle and the and how fast are they moving. Today we assume the maximum range, and we assume that p squared c squared is smaller. So we just consider the Einstein's formula, or the rest mass of the pile. That's a good question. Thank you for the question. Any more questions? Guys, remember that also participation is very important. So let's stop here for a little while and understand the issue of, it's called the strong force, right? It's called the strong force because it dominates. You have protons put together in a nucleus. The Coulomb force will eventually get stronger the more protons you add. But this is why they call it the strong force, because at the distances that we are talking about, distances between proton and neutron, neutron and neutron, so proton and protons, if you put them very close to each other, around 1.5 or 2 Fermi, they have a very strong attraction given by that potential. If you keep putting them closer and closer to about 0.3 Fermi, then they repel each other. And this is, it goes actually, another point, very important point, it goes to infinity as we go to very close distances, right? It goes to infinity here. And these infinities are really a big issue in nuclear physics, because these infinities implies that we have a big problem when we try to apply perturbative methods to nuclear physics. It's important actually that we go through and obviously we won't understand fully the colloquium I gave, but if we go to the NIFEX webpage, let's see, let's type my name there. Let's see what we have here. Registration up here, the one. Videos here. Here's the one. So this explain in detail the problem with the nuclear force, the nuclear many body problem. You know, we are dealing actually in this first slide of the first snapshot of the presentation. We are dealing with a system of particles which are neither small enough to allow direct solution by meaning of the Schrodinger equation. Quantum mechanics is you have a system of 12 particles, a nucleus is carbon 12, you have a system with 100 particles, and this has no way to be treated mathematically using quantum mechanics. You're going to solve the Schrodinger equation from first principles, it is called, for a large system as large as say oxygen 16, without using approximations and different tricks, nor large enough to make statistical methods highly accurate. You know, to apply statistics, you need lots of numbers, and the nucleus has a small number of proton and neutrons to make any statistical method highly accurate, and which, more importantly, interacts through an interaction that has not still not pinned down to any definite form, right? So I will go through this presentation at least from the beginning, or read it, you know, go through it fully and whatever you can understand, because this I'm giving you here the bigger picture of nuclear physics. Okay. So now I want to move and start with this plot and go to the simpler case scenario. This is assignment. So in these lecture notes, again, you have assignments, concepts, right? You have been doing some of these guys. The size of the nucleus, this already you have done, or you are doing it for today's assignments. This one in particular, there will be other problems. Deduce the range of the nuclear force using the uncertainty principle. Binding energy curve, but you have the excess mass is given here, and the formula for the binding energy. As you know very well, this is delta E, or energy is basically the change in masses of whatever you have before and whatever you have later. This is another question, calculate atomic masses. And this is another assignment that you have in your, is due today at 11:55 p.m. or 23:55. So now we move to the deuteron. You see, we move to the deuteron, and we are going to assume a limitation of our knowledge. And we are going to apply our quantum mechanics. We have done lots of potentials with Professor Choconte. And so I want to tell you one thing. So we have here the nuclear potential. And here is the repulsive core that is very difficult to deal with. And then we have the negative part, which is the attractive, and this is the positive part. So here we are going to assume an approximation again. I'm going to assume that we have everything is nicely explained in the lecture notes. Step potential, right? So what I want to mention in this plot is that the negative, which implies attractive, it means that the energy levels of any nucleus are, if the nucleus is bound, any energy levels will obviously come in the attractive side of the potential somewhere. This energy spacing, we'll discuss that later. But basically, a nucleus gets excited generally from a ground state. So ground gets excited, and you have different excitations different excitations here, 6 plus, whatever, and they decay by emitting gamma rays. We'll go through this a little bit later. Now it's a little bit too early. Just want to introduce the concept. This is a typical nucleus, like for instance, 178 hafnium, or whatever nucleus. You have a rotation. This is called a rotational band, and these are the states basically that you have here. This will be the lowest one will be the ground state, which is the more attractive state, and this energy corresponds to the binding energy of the nucleus. Okay, so and now we go to the lecture notes and see what happened with the deuteron. So whenever, as I mentioned in the introduction to this chapter, whenever we don't know, we're not sure about the nuclear force, we go and study the simplest case scenario, which in this case is the the proton-neutron system, which is called the deuteron, or is given by this symbol here, 1 proton and 1 neutron, right? So that proton and that neutron are bound, and this energy here is actually the minus binding energy that you can calculate using this formula, and you know how to do it now. Basically, you get the mass of the deuteron from the tables I provided in chapter 1, minus the mass of the proton minus the mass of the neutron, and you get that B, the binding energy, is minus 2, or 2 actually, 2.2 here. So the binding energy of the is 2.224, something like that, 224 MeV. 2.224. This is in units of MeV, and this will correspond to a state, a bound state in this potential, which we call it here, and this would be an energy of minus 2.22, because the energy of the system is minus the binding energy. Okay, so this will be the system. We have a potential. In this case, we're taking a step potential, which is defined, as you know, from quantum mechanics. So we're going to learn. We're going to go back to quantum mechanics, and by knowing the properties, what we mentioned, nuclear physics is about data. It's about what you measure. You have a state which has a spin, a total angular momentum, and a parity of plus. So knowing this, we're going to deduce. This is everything we know. Everything we know comes from the web page I want to show you here. It's called the National Data Center. It's in Brookhaven National Laboratory, but there are many people involved. And here we have all the information given for any nucleus. So for instance, if we click here, ENSDF, this is the link, ENSDF. We can check any nucleus that you want, and you will see all the information. Let's say carbon 12, and you select all the different studies which have been done before. You see all these studies have been done throughout the years to study carbon 12. And we just get the PDF and carbon NMC. And here we have a PDF with all the information that we have for carbon 12. Okay. Same thing, let's apply it. Let's see whether we have the deuteron is very simple. Hopefully it's also there. And search adoptive levels. having deuteron, see, open here. And this is the information I'm talking to you about. We have a level which is referred as zero, but it's never, there's no zero energy. Here is just to refer the N and the C takes the first level at zero, and then the next one is related to that zero. But this is remember that in quantum mechanics, again, because of the uncertainty principle, there's no such thing as energy zero, and there's always this zero actually corresponds to that binding energy of minus 2.224 MeV, and this is the spin and parity of the angular momentum and parity of the deuteron. Basically, this is the information that we have, and with that information, we are going to deduce properties of the nuclear force. So let's go and have everything here. So we have a potential, which is defined by this. So it's become zero here. And then we have a state, which is a J equal 1 plus, and has energy of minus 2.224 MeV. Now you can realize here that we have removed this positive core because it's very difficult to treat mathematically. It goes to infinity, and as we know from infinity, once you want to apply quantum mechanics, the Born approximation, or if you want to apply any infinities, will be impossible to deduce from perturbation theory, or creates a lot of issues, and we need to somehow, normally people renormalize, but I don't want to go into details on how to do this. You can again go to the colloquium and ask me questions about this repulsive core, but we're going to ignore that for the time being, and we're going to focus on the properties that are coming from data. Coming from data, we know this is the case. The masses of the deuteron, or the proton and the neutron, and we know this state which has these properties. Total angular momentum, J, which is equal to L plus minus S. And this is a formula that we'll use later on. But this, as you should know, is the angular the orbital angular momentum. And this here, S, is called the spin, or the intrinsic angular momentum. Okay. So the total J is equal to L plus minus S, and we're going to deduce some properties of the nuclear force. So I want actually you to go through the lecture notes before I explain anything further, and you are going to deduce what is this, the depth of the potential, which we're going to call it V naught, for the simplest nucleus, a proton and a neutron, to be bound. So what is not V naught? What's V naught? So what is the strength of the nuclear potential? V naught to bind the deuteron. Which again is composed by a proton and a neutron. This is the simplest case scenario in nuclear physics. And as I say, when you don't know about more complex systems, the best thing is to go to the simplest case scenario. So now, as it is written in the lecture notes, you will have to go and remember the wave function. You're going to make a substitution here in the radial part, and you're going to there's some assumptions here. Let's assume that L, which I mentioned before, J is equal to L plus minus S, is equal to 0. So you can get rid of this term. And then you're going to solve. This is going to be the Schrodinger equation that you have for the deuteron. Very simple. And obviously, the conditions for the deuteron is that if R is less or equal than R, this is what R is. This is the radius of the nucleus, basically. If R is equal, less or equal than R, then we have this condition here, minus V naught, which is the depth of the potential, right? And if R is greater than R, then V goes to 0, right? So these are the conditions. V goes to 0. Here you go. So basically, you're going to solve this, assuming this, and assuming the typical control conditions of continuity, right? That you know very well from quantum mechanics. So again, we are applying quantum mechanics for you to learn more about the nuclear force. The whole thing is not explained fully, and you need to be able to solve this problem. Here is the apply the continuity conditions and calculate V naught, and consider that you know the radius of the nucleus is R equal to 2.1 Fermi, which you can calculate again from the 1.2 A to the 1/3 formula, right? So you can calculate that yourself. And I want this to be written as an assignment, the full calculation. And this is due on Monday at 11 o'clock. So solve and calculate this concept 5 here for you to remember. And it's clearly now stated that apply the continuity conditions and calculate what is V naught at that radius. So there are some development of the problem, but the rest you need to do it yourself. Okay. So I think we're going to leave it here. Tomorrow, if you have the problem solved by tomorrow and you can show it, that will be very, very good. I will appreciate a solution by tomorrow. But the problems that we submit on in the assignments, they must be fully developed. I want explanations, I want calculations, you know, everything must be fully developed. And I say that clearly now, that I don't care about the solution. I just care about the process, how to reach that solution. I always care about the way of your struggle, of your understanding to reach a solution, and not about the solution itself.